Okay. Well, I'm going to talk about the model itself. I know you guys watched some videos. I'm going to try to talk about it in a cursory way, give you examples of how it was designed, examples of output that it produces, how we create forecasts from SCRAM, because just creating a PDF of one particular parameter doesn't necessarily give you a good forecast. I guess it could, but we can do better than that. Example forecast output from a few events. Ideas of where I want to go with this project and where I think the future holds for it, and then I'll just review yesterday's event from a SCRAM perspective so you can see what it produced. Okay, so again, you guys already watched the video, but I'm just going to review it again. Imagine there's a lightning strike there southwest of us. That's the red crosshair there. Just knowing that, you know, that there's a thunderstorm there in, I think that's Grady County. What's the probability of severe weather downstream? How would you come up with it, whether you're a great meteorologist or if you're just grandma at home? How would you know whether there's severe weather downstream of that? That was my thought process. How would I know? What pieces of information could I do? If I start with the lightning strike, what can I use to move forward? You know, there's only so many things that you can potentially use to come up with a probabilistic forecast of severe weather. So I gridded it at a 40-kilometer grid scale, and that's roughly what that box would suggest. If there's 1,000 lightning strikes in an hour in that box, it's still, that grid box is now declared as a lightning grid box. So let's figure out what the risk is of storms downstream from that grid box. I capture all of the best analysis data I can get from that grid box. There were 50-some parameters, CAPE and shear and helicity and lapse rates and precipitable water and low-level moisture and dew points and anything you can think of that a severe weather forecaster might want to have on his palette if he's painting the forecast. What do I put all in there? So I gather all these parameters for right now, not for 2 hours into the future, because you know that adds a whole other layer of uncertainty in terms of will the models get it right and all that stuff. I just want to know right now, observationally, what are all the parameters showing? And so this is our best guess for the actual environmental setup. And then I use the bunker storm motion, not Ryan Bunkers, Matt Bunkers up in South Dakota. He developed this idea of computing a statistically reliable way of predicting supercell, right-moving supercell forecasts. And so now I have a vector, and I know from the center point of the grid box where will this pseudo-storm, assuming that any lightning strike in there is represented by that vector, where will it be for the next 2 hours? And then I draw these 40-kilometer range rings. 40 kilometers was arbitrary, but it was based on the size of our grid box and some other reasoning in terms of what might come downstream. And so that solid shape is the envelope that I'm going to look for reports in the next 2 hours to determine if severe weather actually occurred downstream. And in this case, there were hail and wind reports downstream, no tornadoes. And so in this one, whatever parameters are there is now correlated to hail and to wind for this one case. Now imagine doing that for every grid box with lightning for every hour of every day for over a decade, all over the United States. Millions and millions and millions of grid boxes. And so for every grid box since 2006, if there was a lightning strike, I know what was the CAPE, what was the lapse rate, what was the whatever. And then I also know how many hail reports occurred downstream, how many wind, how many tornado, how many SIG-TORs, all of that information. How many occurred if there were 100 strikes in the grid box? How many occurred if there were reports upstream by an hour? I mean, I just tried to create the kitchen sink in terms of parameters. And I think the whole thing is, I say several million points. It's probably approaching 4 million now because we're, every day there's a lightning strike somewhere. That's another grid box that gets thrown in every hour. So it's amazing how rapidly it gets larger. So here's, for instance, some baseline information out of it. Out of those 4 million grid boxes, if you get a lightning strike and you don't know anything else, there's a 0.6 probability of a downstream tornado from that thunderstorm. 6 out of, I guess, 1,000 events or thunderstorms produce a tornado. 4.7% for wind, 3.9% for hail. And so just based on that, whenever we forecast thunderstorms and we don't go 5% wind, for instance, that's a forecast. We're actually saying, you know, even though CLIMO is almost 5% that it will be, we're saying it won't be. Thought went into that just as much as putting a 5% in. And then the same 4% for hail. To say there won't be hail, you have to have looked at some things and come to that decision. It's not just as simple as always assuming that there won't be. And again, this is 2 hours downstream within the envelope of each grid box. So one of the most important things about SCRAM is that most systems don't include results that didn't produce. They don't include null cases. So our system includes every lightning grid box that does not result in severe storms. That's because of the data size of it. Most people have never even attempted to do something like that, to think about every lightning strike that wasn't a severe report. But a lot of those have big CAPE and big shear and all of these really good parameters. And it's impossible to get a baseline climatology of thunderstorms if you don't look at all the cases that don't produce. Our study does. And I think it makes it a tremendously more valuable case study by doing so. But it was a lot of work, and it's really hard to access the database. And doing a query on the database takes a long time because it's got to crunch through all those numbers and stuff. So here's an example output. This is MU CAPE. And this is one that was in the talk that Ariel gave and the videos that you watched. But you can see that in general, there is a slightly increasing probability of severe the more CAPE you have. And you would see this with ML CAPE or SB CAPE or just about any CAPE parameter. A little more CAPE means a little higher probability, but not a lot. It's a pretty flat slope. Basically, this just verifies, yeah, that we've always looked at CAPE. We've looked at CAPE for 70 years at SPC and cells, and it remains something to consider. It's not particularly useful by itself, but it is important. Another thing that we can do with SCRAM that I don't know if you have seen before are these BoxWhisker charts. So we can, for instance, this is for hail. When you look at CAPE, there's some signal there that more CAPE when there is hail. This is only considering those cases that do produce hail. You know, the BoxWhisker distribution goes up with SIG hail versus severe hail versus no hail. So that's always good to see that flipping it over and looking at it this way, which a lot of people who publish papers like to see it in this format, it works also. Another example output, let's see, is a complex query. So this is again mu CAPE, but this time I got really complicated. I said, give me only cases in March, April, and May. I only want ones where there was effective shear of at least 50 knots and only in the plains states. And so it changes everything. Now the slopes are a lot different. And you know, for instance, look at the green line, which is the risk of hail, versus the blue line, which is the risk of wind. Once you get up above about 1,500 joules per kilogram of CAPE or something like that, the probability of wind doesn't really change much. But the hail one, you know, is much higher and continues to increase at least somewhat, even with high CAPE. There's all kinds of nuances in these signals that we're still trying to learn about and figure out how to use them. Yeah?
Sorry, what is the lightning decrease with increase in CAPE?
That's the occurrence of lightning. So it's the rarity of thunderstorms in various CAPE. So most thunderstorms occur, you can see on the curve, about 750 CAPE. So that's the histogram of lightning occurrences. And so it just shows that really high CAPE is rare. And yet, even though it's rare, the probability of a severe report in it goes up. at least in the spring with a lot of shear and in the plains, which is what this plot is. And so I'm just trying to kind of show you that we can slice and dice SCRAM output and do all kinds of crazy stuff with it. And it leads to all kinds of ideas on how you could use this to forecast, or how it could be useful to forecasters by giving them output like this. Now here's the same query. I'm just showing you that that was just for the plains. And the same way, the distribution for hail shows a nice separation between, for instance, no hail and SIG hail. They almost don't overlap at all in the BoxWhisker chart. So there's a strong signal for mu cape in the plains in the spring with a lot of shear for SIG hail. So the question is, what approach would we use a statistical model like this to develop a severe thunderstorm forecast? And you know, there's 50-some candidates in the database, and some of them wouldn't necessarily correlate. For instance, we could come up with a very reliable, statistically reliable model that said, based on the time of day, what's your probability of a tornado? You know, I think we all know most tornadoes around here are in the late afternoon and evening. If you were to plot it, I'm sure there's a real nice spike, because we hardly ever get nighttime tornadoes here, or early morning tornadoes or something. So maybe, you know, let's say that's our first parameter, is just time of day. It's not even a meteorological parameter, but it would show some skill. And if you did it over 6 million data points, you'd realize, wow, that's a really reliable forecast. If I was to only do the southern plains and only in the spring and do a bunch of geographical stuff, I could make an interesting tornado forecast parameter just using your watch. But that doesn't really have plausible causality. The time of day doesn't cause tornadoes. It's a correlation, but it's not causality. And so the idea is we try to find parameters that actually make sense, because over a database this large, almost anything I throw at it, I'm going to get a nice reliable curve. But that doesn't mean it's useful. It just means that, okay, at 5 p.m. here in early May, risk of tornado is higher than it would have been at 9 a.m. But so statistical models are so easy to twist and make into things that don't need to be. And I think it occurs in all sciences and everywhere. When you hear people talk about statistics in medicine or anything else, you probably need to know who's paying that person to say it, because you can make a model to say anything. So, statistical correlations of ML, LCL with hail. If you know much about LCL height, there should be no correlation whatsoever. It's a parameter that's really useful for tornado forecasting, but it means nothing for hail. And SCRAM bears that out in that it's just a flat line. So, if you look at the BoxWhiskers, they all overlap. There's no discrimination between cases with no severe hail and SIG severe hail, and so forget that. That's, you know, the probabilities hardly change at all, and it doesn't make sense that it would anyway. So just, that is not a good parameter to use if you're trying to forecast severe hail. Surface dew point. Same thing. You know, if you look at the histogram lines, which are the faded ones in the background, there's definitely a range there when there are thunderstorms that most thunderstorms occur with surface dew points between about 50 and 70. And there's just the slightest bump through that. But other than, if you really think about, well, I guess higher dew point means there's probably higher CAPE, and if there's higher CAPE, then that might lead to higher dew point or higher hail probability. Well, we should probably use CAPE then. Don't use dew point, because you could start going down weeds that don't make any sense. Let's stick with what really matters, not these second and third level correlations. So same way, very little signal there. That's not a good parameter for forecasting hail. Mu CAPE, we already talked about it. For hail, there's not much signal there either. It's pretty flat for hail over the whole US and for all cases. This one doesn't necessarily make sense. To me as a forecaster, that should correlate. And so we use something called expert elicitation, which Ariel had in the talk also. The idea is people that do this for a living, they probably know what parameters should work. And even though this one doesn't look very good, I need to find a way to use it because it is important. 70 years of forecasters looking at it have told me it's important. And so even though the signal's kind of weak, I'm going to leave that one on the side. I'm not going to throw it away yet. Effective shear, nice strong signal. The curve just has a nice slope to it. There's a lot of discrimination in the BoxWhisker between severe and sig-severe hail. This one clearly needs to be in there. And so for hail, for the SCRAM forecast model, I actually combined the two. And so that's a good one. So we go back to mu CAPE. If you take the product of CAPE times shear, which is sometimes called the Craven-Brooks Severe Hail Index, there's other things, you actually get a nice steep slope on the blue line, which is all hail reports, in the area where thunderstorms commonly occur. That's really important too. If you have a parameter that says, wow, the probability is really high, but you only get it once a year, that's not real useful. You want it to be discriminative in the zone where thunderstorms actually happen. So the slope being way over there to the left is useful, and so you're able to get a really good parameter out of it. So CAPE times shear, mu CAPE times shear, is a really good hail predictor. It's probably the best one I've found. But then I added to that quite a few other parameters. Here are the actual components that go into the SCRAM forecast system. So like when Ariel was showing the tornado forecast from that case in Indiana, it uses STP, the 3 kilometer above ground level, ground relative wind speed, and then it also knows whether it's summer or cool season. So the June through October period is taken separately than the other. After months of trying different parameters and plugging them in and attempts using expert elicitation, that was what I came up with. And then you can see the same for wind and hail and any severe. So these are parameters that SCRAM verifies and my experience has found are useful for these particular threats, these outcomes. And so that's the basis of the SCRAM forecast model. Here's how it verifies. It's remarkably reliable on a year-to-year basis. So I independently verified each year from 2006 to 2015 by subtracting that one out of the learning database and then using it as that 1 year as how does it do. And so the green area is the envelope. So any line that's right up against the diagonal dashed line is reliable. And so if for instance, if you look at the upper left, the tornado probabilities, if SCRAM says there's a 10% probability of a tornado, the outcome is probably 10.5 or 11%. Over millions of cases, a decade of time, it's very reliable. And that's using those parameters I just talked about, the STP, the 3 kilometer AGL wind speed, and the season, and I forget what the other one was. I guess that's it. Just using those 3 parameters. And it actually produces higher probabilities reasonably often. That's part of the design of the system, is that unlike time of day, whereas a max might be a 0.1% or 0.2%, it actually gives you good high values when it needs to. And the same for hail and wind. So it turns out the SCRAM forecast concept of using this stuff, it actually works. And that's exactly what we wanted. So let's look at one example. This is from several weeks ago, February 28th. It was a pretty big tornado outbreak, Illinois, Indiana, and so forth. These are tornado probabilities. This is at the beginning of the event at 20Z, and I've turned off all the grid boxes that don't have lightning. So this is these are unconditional probabilities. Lightning is occurring in those boxes. So you can basically look at each one of those as an actual probability of a downstream tornado in the next 2 hours from that grid box. And these verify very reliably. So there's the forecast. We had 1 tornado in that hour up there near Davenport, Illinois. And then the next hour, you can see, you know, pretty reasonably high probabilities around, and that's where the tornadoes occurred in the next 2 hours. And then there's the next hour, whoops, and that's where the tornadoes occurred. But you can see that area south of Little Rock and south of St. Louis both starting to ramp up. So then the next hour, there's the probabilities, and that's where the tornadoes occurred. And then the next hour, probabilities, whoops, tornadoes. And then the next hour, tornadoes. Now, like in this case, you see up there in northern Indiana, they're occurring in 3% probabilities. That means 97% of the time, using the parameter set I've got, that environment didn't produce tornadoes. It doesn't mean there won't be tornadoes. It's a statistical model. It's not about getting 100% it's going to happen or 0 it isn't going to happen. This is all about predictability. Those tornadoes are occurring in an environment that I as a forecaster or SCRAM as a statistical model would say, wow, you know, that's really unexpected for there to be tornadoes up there. But that happens. And it might be because the parameters weren't representative. It might be because the tornadoes are occurring in ways that we don't understand very well, or at least they're occurring in rare ways. So it's really important to look at it from the perspective of high values means it's more likely, but it doesn't mean it's for sure, and low values don't mean it won't happen. And then the last hour, you can see it continue to produce. That area down in southern Illinois produced a long track EF4, I believe. Anyway, oh, and you'll notice that it started ramping up there south of Kansas City those last few hours, and then we started getting tornado reports back there as well. Okay, so here's the reliability of the system of the equations I talked about, the forecast system. So it's only been running since November, and this is through mid-March. The reliability diagram shows that, for instance, hail is very reliable. If it says there's a 30% probability of hail, in this case it actually goes 40% occurrence rate. But that's because it's rare, it hasn't settled out yet. Everything down from 25 down to 0 is almost right on the reliability line. They're very good forecasts. Tornado, same way. It's surprising because we're talking about November through March, a really poor time for tornadoes. That's not when I would want to verify a statistical model and then show it to a bunch of people about how good it did, because chances are it won't. It did. It actually did a reasonably good job. I'll say a very good job with tornadoes. If anything, it under-forecast wind, which I was surprised by. And it's probably due to the clustering nature of wind, and once things roll, they go long past where I would necessarily expect them to. There's a lot of microphysical and storm scale things that caused widespread wind. And so once it gets going, it results in an under-forecast. SCRAM has a lot of advantages. It has a lot of disadvantages too. I don't want you to think this supersedes all the other data we have and satellite and radar and basic models. I mean, this is just one tool. That's all it is. But using this concept, we can get it down to the storm nature. And I'm hoping in the years to come on radar displays around the nation, and especially in front of warning forecasters, they'll be able to click on a storm and get the SCRAM probabilities right on it, because it's down to a 40-kilometer grid. So there's this storm out there in southeast New Mexico on this particular day, and you know, a fast computer could just query what are the probabilities for this lat long. There's the storm, and plot them for the forecaster to know that, oh, you know, there's a really good chance of hail on this for the next 2 hours. I need to be watching for when that hail core gets going on radar and jump on it early. Don't wait, because I know the probability of hail is high. And all of this is just from statistics. It's not looking at radar. It came up with that answer long before the radar started showing tough stuff. So SCRAM is statistically reliable. It produces explicit forecasts of hail, wind, and tornado. No computer models do that. It's probabilistic output, which is the future of meteorology. We don't do solid You know, it's going to be a tornado or it's not. Probabilities are the way we're going. It's a very, very large learning data set, and it's a brand new approach. And I really like that as much as anything. It's a new approach. So many other things are a slight deviation off of what we've done over and over and over. This is a brand new approach, and I like that about it. But there are definitely limitations. It's a statistical model. It's going to be wrong sometimes. It's going to have bad input data. It's going to be designed poorly that could be improved. It'll need updates every once in a while. All of these models that we get, if one of them isn't performing very well, we'll note it as a forecaster, but we won't throw it away next time. We'll look at it again and again and again. We don't ever throw away models just because they did poorly on a particular day or something. It's just a model. I don't expect to get it right all the time. New methods require time to learn, and we're still learning at SBC. We're trying to figure out how much can I rely on this output? Can I trust it whenever it's saying the tornado threat's going down? Do I actually try to use that in a forecast? I don't know yet. It's only been running for 4 months, so still learning about it. And it's only as good as input data, and we know that's flawed. We have so little observational data in the United States, and we've got the best in the world. It is definitely limited, and there are times that it lets us down. So let's just think about creating statistical models. And let's just imagine if you were to create a set of models to predict whether a person will get an A in this class. You know, what would you use as input for that? And let's assume that the model we're going to produce is reliable. Okay, we've got a big enough data set. It's going to be reliable. So here's model number one. It's going to use test scores. You give it the test scores of all the tests in this class, and it's conditional upon you putting out full effort for the final and not blowing it off and getting drunk the night before. And it will provide you the day before a final, it'll hand to you the probability that you're going to get an A in this class. The range is 0 to 90% that it's reliable at. So whatever number it gives you, it's probably pretty good. That's useful information. If you really need to know if you're going to get an A, it's a little late. If it's going to give it to you the day before the final, what can you do about that? You know, if it's too late, you can't get your money back for taking the course. You can't drop. It's way too late for all of those things. It's useful for some things, but its utility might be lower for others. Depends on what your need is. Here's model number two. Maybe it involves how much do you study. And so it needs to know how many hours are spent studying for this particular class. You have to have studied at least a minimum of 10. And it needs to know your first 2 test results. And so it won't give you a result until after that. It says it'll give you a result 30 days before the final. Okay, well, we're getting better. It's probably still too late to get your money back, or I don't know, maybe to drop. I don't know how OU is. But you notice the reliability goes down a little bit because you're not using as much data. You're not right up to the end result. And so you can't have reliable output or confidence as high because it doesn't have as much input. And then there's model number 3. And all it looks at is your college transcript. All the classes you've taken before you even enroll in this class. And you have to have gone to school for 2 years. And before you even enroll in this class, it's going to give you a reliable estimate of whether you can get an A in this course. The reliability goes down. Maybe its max forecast is 70%. But that might actually be useful to you. You know, if you're trying to really maximize your GPA and stuff, and you had this kind of statistical model for all classes, then you could real quickly, based on my college transcripts and stuff, I know which I'm going to succeed in. Those are the ones I'm going to do. It'll keep my GPA really high. I don't have to spend any money up front, and it's a reliable model. That's the SCRAM method, because we're conditioning on lightning, which is when the thunderstorm first forms. We don't know what the rotation couplet's going to look like. And we don't know if it's going to be a bow or a supercell. We don't know if the mesh core is going to get strong, or we don't know any of that stuff. All we know is there's a lightning strike. This is an approach of looking at something before it even really starts and developing a statistical model down to the storm scale. And that's what its power is. It isn't going to be as reliable as a couplet on radar. There's no possible way it could do that. It's not designed for that. This is taking a step back and look at environment. So there's a lot of ongoing work happening. I've applied it to the RAP, I've applied it to the NAM, I've applied it to the GFS. I'm working on verifying all these things to see how they do, and they're reliable to some extent. So far it's looking good, but a lot of work left to do, and definitely a lot of work before I want to publish and let everybody start using it, because I don't even know for myself how good it's going to be. But that's where we're going, is someday looking at the GFS 240-hour forecast and having a probability of a tornado for each grid box. It'll only be as good as the GFS forecast, but it's something, and it's something forecasters can use. So finally, let's look at yesterday, fresh in everybody's minds. Just to remind you, day 5 issued last Wednesday. We circled that area for an outlook. And then day 4, day 3, day 2, day 1, remarkably consistent. It just shows the predictability of this particular setup. We knew a long time out that this one was going to be focused over south central Oklahoma, north central Texas, which is nice. Then we wrote an MD saying where things were going to be focused, and then we issued a watch. So, you know, the watch versus the day 5 forecast, not a whole lot of difference. I could only hope we could do that more often. This is a rare one, but that's why I'm showing it to you, because we're proud of it. So anyway, so if you remember yesterday, there were thunderstorms that formed early, and I wasn't expecting stuff to flare up that early. But here's the SSCRAM hail forecast for that time period. Really low, 1% probabilities. Now there are a couple 14s, but in general, it was saying there's a low probability of hail with these. No, there was a hail report. One hail report, you know, west side of Norman, back towards Newcastle, somewhere like that. It didn't keep producing anything like that. It was low probability. And then it kept moving along eastward, no reports that hour, low numbers. Same, they're starting to ramp up as we get into the heat of the day and so forth, but they're still relatively low numbers. But then I think the next hour, now the high numbers start flaring up. And, you know, there's 20s, 23, 25, 15, 25 down in Texas. So now these, you know, just popped up out of nowhere, and there's the hail reports in the next 2 hours downstream. So those grid box produced its hail. And then the next hour, now we're getting up into 35 range, 44% probability of a hail report if a storm will form in that one box. And again, these are unconditional. Lightning is occurring. So there's the hail reports based on that. So it definitely focused you in the right place there. And what's interesting is, you know, we were trying to figure out if the tornado problem was much yesterday. And if you use SSCRAM, there's the hail or the severe hail versus tornado probabilities. And that 44% versus the 5% tornado, it said there's a 5.5 time greater risk of a hail report than a tornado report yesterday. From a 5% probability to a 44% probability. And that worked out. You know, there were hundreds of hail reports and maybe a couple tornadoes. It was not a tornado day, by and large. And statistically, using STP, 3-kilometer AGL wind speed, the time of year, and so forth, it worked. This model predicted it would not be much of a tornado day. And then moving on, probability stayed high and shifted down into Texas with a lot of hail reports. And it kept going. And that's all I got.